Hi. There's more. We still have more to do. Today we're going to look at another sort of application problem called related rates. And these are more story problems. And so instead of trying to write it all down here, I'll just type it all up. Let's look at the first one. Okay, so let's talk about this for a moment. So the oil rig is leaking a constant amount of oil into the ocean, which, by the way, is horrible, right? And so a constant amount of oil. So when the oil first begins to leak and the spill begins to grow, it's growing really quickly, right? Because boom, here it comes, right? But as it gets bigger and bigger, the same amount of oil has to spread out over a huger distance. And by the time the spill gets pretty big, it's kind of hard to tell that it's growing at all, right? Because the same amount of oil is feeding it per hour, but the rate at which the sides are growing out is slowing down. Do you see that? Does that make sense? And so that's why these problems are problems, is because the rate that one thing is changing, it's related to the rate that the other thing is changing, but they're all changing. Okay, so the way that you do one of these problems is you draw a picture. So there's my oil spill. And I've written down what's going on in the problem. One thing that you need to do is that you need to find an equation that relates some of the quantities in the problem. And sometimes you have to go look this up. And it depends on sort of the geometrical things that are going on in the problem. Sometimes you have to look it up, sometimes you don't. It depends how much you remember about geometric formulas. So here I need a formula that relates the area of a circle to its radius. And I remember that one. So the area is equal to pi r squared. And so, what is this? This is the rate at which the area is increasing with respect to time, right? Square meters per hour. So, you remember when we talked about dy dx, that kind of notation? Well, we're really going to use it here. So this is the rate at which the area is changing with respect to time. If area is capital A and time is little t, then this thing is dA dt. The rate at which the area is changing with respect to time. Okay? This is just what the radius is equal to. And the thing that we want to know is how fast is the radius increasing? And so that's going to be a certain number of meters per hour, right? And so if the radius is r and if time is t in hours, then the thing that we're trying to find is dr dt. We want to find dr dt when r is equal to 5, and we know that dA dt is constant, and that it's always equal to 3. Okay? I know it. I know. I'm sorry. Here's how you do it. See this thing? Relationship between A and R? No t's, right? There aren't any t's in this because it just has to do with a circle, and circles do not depend on time. But a growing circle does. So what we're going to do is we're going to take this equation and we're going to differentiate the whole thing with respect to t. With respect to t, there are no t's in it, right? That means every variable is treated like an implicit differentiation. We're going to ddt this whole thing, okay? If we take the derivative of a with respect to t, well, that's just dA dt. Over here, if I want to take the derivative of pi times r squared with respect to t, I treat this like I'm differentiating with respect to r, and then I have to multiply it by the derivative of r with respect to t. Do you remember implicit differentiation? If you forget how it works, you might want to review that video before you go on here, okay? Because we're really using a lot of it here. So dA dt is equal to pi times the derivative of r squared is 2r, but I'm differentiating with respect to t, so I'm going to multiply this by dr dt. The equation that I have now, by the way, this equation is called a differential equation because it's got derivatives in it. So anyway, the equation that I have now has three variables in it: dA dt, r, and dr dt. So to solve this equation for any one of the variables, I just need to know what the other two of them are. And so what am I doing? What am I doing? I want to find dr dt when r is 5, and I know that dA dt is constant at 3. So I just plug all of those pieces in. dA dt is 3 equals 2 pi times r times dr dt. Meters, right? Yeah, meters per hour. So the radius is changing at a rate of 0.095 meters per hour at this particular moment. And the assumption here is that as r increases, dr dt is going to decrease, right? Because the bigger the circle gets, the slower it's growing in terms of its radius or diameter. So that's a related rates problem. Let's pause for a moment. I put the steps together for you, so let's take a look at those. So here are the two boats, one traveling to the east at 12 knots an hour, the other traveling to the north at 16 knots an hour, and we want to know how fast is the distance between them changing after 2 hours. So they leave from the same place. So if you want to, we could call this thing A and this thing B, and then the distance between the boats we could call C, and I've chosen those particular variables because I recognize that this is a right triangle, and the equation that's going to relate these quantities is the Pythagorean one, okay? Okay, so what are we trying to find? Find when t is equal to 2. And what do we know? We know that dB dt is 16. And dA dt is 12, and that's about all we know. And we know the relationship between A, B, and C is this one. The most common mistake that students make when they are doing these problems is that they try to plug this in too early. The work that you do at the beginning here is describing the situation between the moving quantities at any time, at any point. And it isn't until you've set all of that up. Do you say, okay, stop the camera, pause, and we want to look at it right at this instant. And that's when you plug everything in. And that's not until after you've taken the derivative, okay? So here we go. All right. So we want to smack this whole thing with a d dt, right? We're going to d dt each part. The derivative of a squared with respect to t is going to be 2a. Then I have to multiply that by dA dt. Okay, and it goes the same, obviously, for the other variables. And just to make things just a little bit easier, I'm going to divide the whole thing by 2, right? Because every term here has got a 2 in it, so just lose those, okay? And so now, oh my gosh, now we have an equation that's got 6 different variables in it. A and dA dt, B and dB dt, C and dC dt. So in order to be able to answer the question, I have to be able to fill 5 of these in to come up with the other one. Which one am I after? This one. So that's the one I'm trying to find. So I got to fill in the rest of this. I know dA dt and dB dt, and so I got to fill in A, B, and C. But it's not too bad because listen, after 2 hours, if this boat is going 12 knots an hour, after 2 hours, it's gone 24 knots, right? A knot is a nautical mile, so you can just think of it as a mile. So at t equals 2, right? So those are pretty easy to figure out. What about C? Well, after 2 hours, if this is 24 and this is 32, I can square those and add them together and take the root, right? And that'll give me the length of the hypotenuse. And 12, 16, 20, it comes out to 40. Okay? So I believe we have everything now. So let's plug all the pieces in. So we need A times dA dt. That's 24 times 12. Plus B times dB dt. B is 32 and dB dt is 16. And that's equal to C times dC dt, so 40. And if you multiply all of this together and you add these things up and you divide by the 40, you get dC dt. dC dt is 20 knots per hour. Do you see how it works? Okay, so in this last problem, we have this pile of sand, right? And this makes sense to me, right? If you just dump sand or whatever into a pile, it makes the shape of a cone, right? So here's our sand pile. And in this particular sand pile, the radius is always 3 times the height. The radius is always 3 times the height, so I have not drawn the pile to scale, have I? Okay, and we know that sand is being added to the pile at a rate of 100 cubic feet per minute. What is this? What is this doing to the pile? Is it the rate that the pile, the rate the pile's height is changing? Is it the rate that the pile's circumference is changing? When we're adding cubic anythings, aren't we increasing the volume, right? So shouldn't this be dV dt if V is the volume? So just taking the problem apart, this is what it looks like to me, right? So we've got R's and H's and V's, and so in order to get a handle here, I need to write down a relationship between all of these things, and that's the volume of a cone. And if you don't know what the volume of a cone is, that's okay. You can ask me, you can ask one of the other people at your table, or you can look it up on the internet. There's lots of ways to get it. I don't expect you to know it, but I am hoping that you'll go find it. Okay, so the volume of a cone is 1/3 pi r squared h, okay? But for this particular cone, r and h are related, so I'm going to get rid of the r because I don't need it for anything. I'm going to replace that the r here with 3 h's. And simplify this. Right, because you get 9h squared here, and the 9 will cancel with the 3 on the bottom and leave the other 3, and so the volume just looks like this. Okay? And so what do we do once we have the equation that relates the variables in the problem? We differentiate the whole thing with respect to t, and it's always t, because these are rates, and that's the change in whatever per unit time. Okay, so it's always d dt. So on the left, I get dv dt. Over here, if I pull this 3 down to the front, that'll give me 9 pi h squared, and then I have to multiply that by dh dt. Okay? 9 pi h squared times dh dt. Okay, notice that I've ignored this thing, right? I'm setting up the problem and working it through so that this will explain what's going on at any time. And it isn't until almost the very end, after the differentiation, that you plug in the instant that you're interested in. And so that's what I'm going to do now. Okay. So at the moment when h is equal to 8, dv dt is 100, right? So here's 100. So solving for dh dt, we get this, and I punch this in before I turn the camera on, and it's about this much. The units on this is the change in height per unit time, and we're dealing in feet here, so this is going to be feet per minute, right? Minute per minute, feet per minute. Okay, so that's my spiel on related rates. If you have any questions about this, bring them to class or get a message to me. I hope you're having a great week, and I'll see you soon.